Okay, now I'm going to talk about Denavit-Hartenberg parameters, which is another way of analysing kinematics of robotic mechanisms. So we know that a manipulator is built up of chains, or a lot of them are built of chains of linkages connected by joints, and we start numbering them from the base, which is generally considered link 0, right all the way to the endpoint, which could be link n. And what we're going to see here is, rather than have to come up with some general transformation matrix to align the frame and then a shift in order to move the origins and then another rotation in order to account for the rotation round the joint, it's actually possible, if we put frames together in a careful way, to actually come up with a representation in terms of 4 parameters which will actually capture what we want to know about the linkages. And these 4 parameters are going to be link length, link offset, link twist, and joint angle. Or it could also be, of course, displacement when we have prismatic joints. And the argument is this is a bit more readable than transformation matrices. That's certainly the case. And it was come up by a couple of guys working, I think, at Stanford University a while back. Denavit and Hartenberg. As is always the way in life, there's actually, unfortunately, 2 conventions which are used for this. We're going to be using the conventional approach to Denavit-Hartenberg. I think it's actually a bit easier to understand, so we're going to stick with that. Certainly there's much more material out there on the internet and in books on conventional representations of robots using DH parameters. If you try doing modified, you have to slightly do the analysis. You look at things in a slightly different way from another perspective, and there's, in my experience, very, very little information out there in the internet. So, if you're building robots and you want to, very rarely do we come up with a novel design that's completely not been done before in terms of a kinematic design of an arm. So sometimes it's nice to see, have you analysed the bits of it correctly by comparing it with other people have got. So that's, I think, a really important reason for sticking for the conventional. And the conventional basically means that the x-axis is going to intersect and is perpendicular to the previous z-axis. That's what we're going to go along with. And we're only going to talk about classical because I don't want to give you 2 different ways of doing things then lead to confusion. So, the Denavit-Hartenberg rules. So, basically, it's a way of calculating the homogeneous transformation that will take you between linkages, right? So, having calculated these transformations, we end up with homogeneous transformations just like if we did it by hand, and because of that we can just build up overall kinematic chains just like we did before, because we still end up with homogeneous transformations. We're just getting them in a slightly different way than maybe looking at it from first principles. So just like we did before, if you want to work out the overall forward kinematics 3 to 0 of a mechanism, we can actually do it in stages, go 3 to 2, 2 to 1, 1 to 0, and multiply them together because they're homogeneous transformations, and that's the beauty of it. But we do have to be careful how we assign the frames, but we've already been kind of using that approach anyway for this module, just to make life easier. So let's think about why we want to do it that way now a bit more, and go through the rules that they come up with. Having come up with these parameters, we'll be able to then put them into formula directly if we wish to do so, or you might want to build it together a little bit more from first principles. Basically, we have to construct a table for the 4 parameters for n-1 frames. So if you've got 2 frames, right, transformation between 2 frames is going to give you 1 homogeneous transformation. So we always have n-1 entries. So 4 rules for classical DH are as follows. For a revolute joint, the z-axis is placed along the direction of rotation. So in other words, if the thing's got a rotary joint, then the rotary joint axis has got to be used as the z-axis of our frame that we want to put on there. Now, if it's prismatic and it's moving in and out, then we put the z-axis along the direction of the movement instead. Now the x-axis that we then put on has got to be perpendicular. That means at 90 degrees to the z-axis and also the previous z-axis. That's very important. Having specified z and having specified x, you have no alternative but to use the right-hand rule, in order to make sure that you put the y1 in the right way, right? And I would recommend either doing it with the right-hand or by hand, or using some little kind of little frame that you construct, just to make sure that you don't put something in the wrong way round, because it's very easy to do otherwise. So xn, so the x-axis has got to, like I said, has got to also intersect the last z-axis as well. And it becomes a bit clearer when we start looking at what these actual things mean. So I've got this overall drawing here, but I'm just going to explain a little bit more detail, maybe using these diagrams. Basically, if you look at this, if you look at the z-axis on this, there's a z-axis here, because there's going to be this is a rotary joint, of course. This is going to be another rotary joint. The angle alpha then, right, is basically, it's the twist of the system. It's how much you have to rotate to align the z-axes from two particular joints that are which are separated by the link. So if this is z-axis is going straight up, we see in this case this one is pushed over slightly, rotated around the x-axis, but it's rotated by this angle alpha, right? So this is, again, looking at that rotation around the x-axis by an angle alpha. So basically that gives you, this alpha gives you the alignment that you need in order to make, you know, how much do you have to rotate this one in order to get it to line up with the following one. So it's this rotation twist, if you like, of the joints. If it was a planar mechanism, it's going to be 0, because they're going to both be pointing in the same direction. And if it was one of these a revolute base, where you've got, first of all, you've got a vertical axis coming up, and then the next one is going to be at 90 degrees to that, then we're going to have an angle of about, well, typically 90 degrees. The only thing you have to be careful with is when you're looking at the angle to make sure you're using the right-hand rule to get the positive sign or the negative sign. Right. So the length R. So the length R, or A, basically is going to be, it's called the length of the common normal, but basically what it is, it's the length, it's the length between the two z-axes, right? So if this was lined up now, and this is obviously going off at a slight angle alpha in order to demonstrate what alpha is. If it was straight up, then the A would just be the distance between the two, and if it's rotating around, let's say rotating around this first joint here, it would represent the length of radius of rotation of this second axis around that point. That's also why it's sometimes called R. So the angle theta then, this is another rotational angle around, this time, the first joint, right? So it basically says how much do you rotate around the first joint to align the past x-axis with the new one, right? So by rotating it by theta, and we're rotating it around by theta here, we can align what the x-axis of the second frame is with the first frame. Basically, that's what it comes down to. And this is typically the in a revolute system, the theta is going to be the control variable. This is the thing that the mechanism is changing in order to actually get you to do something with the robot. On the other hand, like things like link length is actually the length, it's the length of the bit of metal or whatever you're using. And this alpha, again, it's something structurally into the mechanism normally, and you can't change it as a control. Right, so that's basically the alignment. The theta aligns the x directions of the frames. The length d then basically it's just an offset up and down the first z-axis. So how far up and down are you on the z-axis here? And it's just given by d, right? So this accounts for if you've got a planar arm, there won't be any offset. but you could have an arm that's planar, but then it's got bent up, so you've actually got a higher part on the second joint than on the first one, in which case you'd have a D value in there. Like I said, basically the idea of Denavit-Hartenberg is to let you define joints in terms of, in fact, it's on the basis of what's called two screw displacements. So it's going to be a rotate and shift, a rotate and shift. So the idea of a screw displacement is you're rotating round and you're also moving, right? That's why it's like a screw. Actually, you turn a screw, a nut on a threaded piece of metal or something. It rotates round and it also moves in a linear sense. So that's the idea. You've got these. You can break up this thing in terms of a rotation and also a displacement. So let's have a look how we can do this with represent this with two screw displacements. So we can separate screw displacements into basically, we don't have to do them both at the same time. We can consider it a pure translation and a pure rotation, right? So that's what we're going to consider it as being. So we've got our alpha, we've got our A, we've got our theta, and we've got our D. And basically, what we can say is we're going to have the following transformation. First of all, we're going to have this is, like I said, just to get back to what I mean by two screw displacements. We've got a rotation followed by a translation, then a translation followed by a rotation. So the first pair is one screw displacement and the second pair is another one. So let's just break that down into what we need to do. So if we want to get from this frame at joint I, or whatever it's called here, to the next one, JI plus 1, first thing we need to account for is the fact we've got this alpha. This thing is twisted round. So we need to rotate round alpha, which is a rotation of alpha. Sorry, not rotate round alpha. Rotate round x by alpha is what I should have said. And that accounts for this alignment of the z-axes. The next bit we have to account for is the shift, right? So we've got a shift. After we've aligned the direction of the z-axes, we then got to move along the x-axis. So we're actually coincident with the previous z-axis. So that's a translation along the x-axis, right? Because we've said that's the x-axis, by an amount A, right? That's that bit. So that's the first screw transformation sorted out. Then what we're going to say is now we're going to do, we're going to do the offset first now. The fact that this could be up and down in comparison to where we were in the other one in terms of along up and down the z-axis. So we move up and down the z-axis by this amount di, or d, in fact, for this particular joint. And then the final thing is, we know that this joint also rotates, right? So this rotates, obviously, around the Z. And basically, when it does so, it basically, what it's doing is it's changing the alignment of its x-axis with the one of the next frame. So we've got a rotation around the Z-axis, that's this bit here, a rotation around the Z-axis by theta, which we've also got to account for. So we've got those four things that we can then basically multiply together. We can easily work out what the rotation axis, the rotation matrix is around x, what the translation is along x, what the translation is along z, and what the rotation is around z. We can just basically put in our homogeneous transformations, and we put in the parameters that we've got for the thetas, for the alpha, for the d, and for the theta. Now, theta, alpha, I, and d. We multiply them out, and this gives us the homogeneous transformation matrix representing the mapping from frame n to frame n minus 1, basically, but you have to put the appropriate parameters in, of course. And if we can map between two frames, just like we said before, then what we can do is work out all of these mappings for all of the frames, adjacent frames, well, here to here, here to here, here to here, for a chain of linkages if we're interested in analysing a robotic mechanism. So we'd come up with a transformation, or we can go through them one at a time. You go through the links one at a time. You might want to do this one first, put in your theta, your alpha, your A and your D. Then you do the second one, the second link. Then you do the third link, and you end up with this DH table, right? We end up with a table. Again, alpha, angle, about common normal. It's the thing that aligns the z-axes. That's the way I remember it. A is the length between them. It's basically, in rotary, in lots of rotary cases, it's going to be the radius of rotation or the length of the link. Then the theta is going to be the rotation around the control. And D is the offset up and down along the z-axis. So a simple, very simple planar example would be as follows. We've got a frame here, we've got a frame here, and we've got a frame here, 3 frames. We can see in this case there are basically there's no twists, right? So all the z-axes will be coming out at you because it's going to be following the right-hand rule, right? So it's going to be, y is going up, x, yeah? So we're going to end up with basically coming towards you will be the z-axis here, here, and here. So they're already aligned, right? So they're already aligned, so the angle between them is 0. So the alpha is 0 here, and its alpha is 0 here. There's no shifting, it's all in a line, so there's no shifting along the z-axis. It's all planar, so there's no D. But what we have got, right, is we've got theta, so we have to account for the fact that we can rotate around these axes by theta here, theta 1, theta 2, and also the fact that the radius then around which it moves is given by the length of the links, which is going to be A1 and A2.